Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. Your website is down. The EC2 instance is healthy. The application is running, and the security group looks correct. But customers still can't connect. So where do you look next? Is DNS pointing to the wrong destination? Does the subnet have the right route? Is there an internet gateway? Does the instance even have a public IP address? Should the traffic be going through a NAT gateway instead? Or is the workload trying to reach an AWS service through the wrong network path? This is where AWS networking becomes confusing for beginners. Every individual service seems simple. The challenge is understanding how they work together. In the next 20 minutes, we're going to connect the entire AWS networking picture: VPCs, public and private subnets, route tables, internet gateways, NAT gateways, VPC endpoints, VPC peering, transit gateway, Route 53, CloudFront, site-to-site VPN, and direct connect. By the end, you won't just know what these services are. You'll know which one solves which networking problem, and how to recognize the answer when AWS gives you a scenario instead of a definition. By the end of this video, you'll be able to do 3 things. First, draw the VPC public and private subnet routing path from memory, including the route that makes a subnet public and the extra conditions an IPv4 resource needs before it can actually use the internet. Second, choose the right connectivity service for 3 situations: outbound internet access from a private subnet, private access to AWS services, and hybrid links between on-premises networks and AWS. Third, recognize the CLF C02 networking patterns that commonly trip people up: route table versus public IP, NAT gateway versus VPC endpoint, VPC peering versus transit gateway, Route 53 versus CloudFront, and VPN versus direct connect. That is the whole video. By the end, you should be able to explain the networking decision, not just memorize the service name. A VPC is a logically isolated section of AWS, where you control IP ranges, subnets, and routing. It's not physical hardware. Think of it as your own private address space inside AWS. AWS sets a default limit on the number of VPCs you can create in a region, and you can request an increase if you need more. A smaller number after the slash in a CDR block means a larger address range, so 10.0.0.0/16 gives you far more IPs than /24. The common mistake is treating a VPC like a piece of hardware you can touch. It's a network definition. One route makes the formal difference between a public and private subnet. A public subnet is associated with a route table that has a route to an internet gateway. In the common IPv4 design, that route is 0.0.0.0/0, pointing to the internet gateway. That gives the subnet an internet path. But a route alone does not make every IPv4 instance publicly reachable. The individual resource also needs a public IPv4 address, or elastic IP address, and its security group and network ACL must allow the traffic. Without those, the internet route exists, but the instance still cannot communicate as expected. A private subnet does not have a route to an internet gateway. Its resources can still reach the internet through another component, typically a public NAT gateway, but they do not accept unsolicited inbound connections from the internet through that NAT gateway. One practical point. AWS reserves addresses in every subnet, so you never receive every address in the CLF block. Plan your address space with that in mind. The route table decides where traffic actually goes. Every subnet's route table includes a local route for the VPC's own CIDR. When a packet's destination doesn't match a more specific route, AWS falls back to the most specific match available. Adding a route for 0.0.0.0/0, pointing to an internet gateway, gives unmatched traffic a path to the internet. The key habit when you're troubleshooting a subnet is to check its route table first. The route table is the control point that determines whether a subnet has a public path or stays private. Let's troubleshoot a real scenario. An EC2 instance has a public IPv4 address. Its security group allows HTTPS, but users on the internet still cannot reach the web application. Your teammate says it has a public IP, so the subnet must be public. Is that correct? No. A public IPv4 address does not make a subnet public. Check the subnet's route table. For the common IPv4 public subnet design, you need a default route 0.0.0.0/0, pointing to an internet gateway attached to the VPC. Now think about the complete path. Route table, internet gateway, public IPv4 address, security group and network ACL. All of those pieces must support the connection. That's the troubleshooting habit to remember. Don't look at one setting and assume the network works. Trace the entire path. An internet gateway is the highly available VPC component that allows communication between your VPC and the internet. You attach it to the VPC. It is not a router instance that you patch or manage. For an IPv4 instance to communicate with the internet, the common setup needs three things. First, the subnet route table needs a route to the internet gateway. Second, the instance needs a public IPv4 address or elastic IP address. Third, the security group and network ACL need to permit the traffic. That is the complete mental model. A public IP without the route does not work. A route without the public IPv4 address does not give an IPv4 instance direct internet access. And neither one overrides a security group that blocks the connection. If the internet gateway is detached or the subnet route is removed, the internet path disappears. Here is the console flow that gives a subnet an internet route. In the VPC console, open route tables. Select the route table associated with the subnet, choose Edit Routes, and add a route with destination 0.0.0.0/0. Set the target to your internet gateway, then save. That is what makes the subnet a public subnet in the AWS definition. Its associated route table has a route to an internet gateway. Now check the instance separately. For an IPv4 instance to reach or be reached from the internet, it also needs a public IPv4 address or elastic IP address, plus security group and network ACL rules that allow the required traffic. So remember the troubleshooting order. Route table first, then public address, then security controls. If you prefer the command line, the basic flow uses three actions. First, create the internet gateway. Second, attach that internet gateway to your VPC. Third, add a route for 0.0.0.0/0 that points to the internet gateway ID. That third action gives the associated subnet a public internet route. But the route does not automatically assign a public IPv4 address to an instance, and it does not open a security group. Those are separate configuration steps. On screen, show the workflow in this order. Create the gateway, attach it to the VPC, then create the default route. In a real environment, verify the current AWS CLI syntax and confirm that you are editing the intended route table before you apply the change. A NAT gateway lets resources in private subnets initiate outbound connections without accepting unsolicited inbound connections from the Internet. For the common IPv4 Internet egress design, you create a public NAT gateway in a public subnet and associate it with an elastic IP address. The NAT gateway subnet needs a route to the Internet gateway. Then the private subnet's route table sends its Internet-bound traffic to the NAT gateway. The traffic path looks like this: private instance, then NAT gateway, then Internet gateway, then the Internet. Response traffic for a connection that the private instance started is translated back and returned to that instance. New, unsolicited inbound Internet connections are not forwarded through the NAT gateway. Do not place a public NAT gateway in a private subnet. It needs the public subnet's route to the Internet gateway to provide Internet egress. One advanced note for later: AWS also has private NAT gateways for private network translation through a transit gateway or virtual private gateway. But for the cloud practitioner Internet egress pattern, think public NAT gateway in a public subnet. Quick check before we move past the gateways. Which service lets an IPv4 instance in a private subnet reach the Internet for updates and downloads while remaining unreachable by new inbound Internet connections? The answer is a public NAT gateway. It sits in a public subnet, has a path to the Internet gateway, and private subnets point their Internet-bound default route to it. Remember the path: private instance to NAT gateway to Internet gateway to Internet. The NAT gateway is for connections that start from inside the VPC. Here is the comparison that causes the most confusion. A NAT gateway is a general path for private subnet resources to reach Internet destinations. It can reach public APIs, package repositories, websites, and AWS public service endpoints, assuming the root, DNS, and security rules allow it. A VPC endpoint is different. It gives your VPC private connectivity to a specific supported AWS service or endpoint service. It is not a general-purpose route to every destination on the Internet. There are two big endpoint patterns to remember. A gateway endpoint is available for Amazon S3 and DynamoDB. It uses route tables and avoids the need for a NAT gateway or Internet gateway for traffic to those services. An interface endpoint uses AWS Private Link and is available for many other supported AWS services. It creates private network interfaces in your subnets rather than a route table target. So the exam decision rule is simple. Use NAT gateway for general Internet egress. Use a VPC endpoint when the destination is a supported AWS service and you want private service-specific connectivity. A gateway endpoint lets your VPC reach Amazon S3 or DynamoDB without a NAT gateway or an Internet gateway for traffic to that service. When you create a gateway endpoint, you choose the route tables that should use it. AWS automatically adds a route to each selected table. The destination is an AWS-managed prefix list for S3 or DynamoDB, and the target is the gateway endpoint. That route is more specific than a general 0.0.0.0/0 Internet route, so traffic for the supported service follows the gateway endpoint path. Other destinations still follow their own matching routes. Keep the scope straight. Gateway endpoints are for S3 and DynamoDB. If you need private connectivity to another supported AWS service, you may need an interface endpoint instead. Here is the CLI concept for creating an S3 gateway endpoint. You create a VPC endpoint, choose the S3 service name for your region, identify the VPC, and specify the route tables for the subnets that should use the endpoint. AWS then adds the S3 prefix list route to those selected route tables. That route table association is what directs eligible S3 traffic through the gateway endpoint. You do not manually add a general internet route, and the endpoint does not automatically apply to every subnet in the VPC. It applies to the subnets whose route tables you selected. On screen, show the endpoint creation command with placeholders for the VPC ID and route table IDs. Then show the route table result, the S3 prefix list as the destination, and the gateway endpoint as the target. Here's a scenario you'll eventually face in a real AWS environment. An EC2 instance sits in a private subnet. It needs to upload files to Amazon S3. It also needs to download software updates from a public repository on the internet. Someone creates an S3 gateway endpoint and says, "Great, we don't need the NAT gateway anymore." Are they right? Not necessarily. The S3 traffic can use the gateway endpoint. That means the instance can reach S3 privately without sending that S3 traffic through a NAT gateway or internet gateway. But what about the public software repository? The S3 endpoint does nothing for that destination. If the instance still needs general IPv4 internet access, it needs an appropriate egress path, commonly a public NAT gateway in a public subnet. So the architecture can use both. S3 traffic follows the gateway endpoint. General internet traffic follows the NAT gateway. That's the distinction you need to remember. VPC endpoints are service-specific. NAT gateway provides general internet egress. Always ask where the traffic is trying to go before choosing the network service. When two VPCs need to talk directly, you create a VPC peering connection. It's a direct link between two VPCs, and each side needs a route table entry pointing at the peering connection. In practice, you plan the IP ranges so they don't conflict. Otherwise, routing becomes ambiguous, and traffic can't be forwarded correctly. The biggest trap is that peering is not transitive. If VPC A peers with B and B peers with C, A cannot reach C through B. Here is the operational distinction. VPC peering is a direct connection between two VPCs. It is a strong fit when you need simple, one-to-one private connectivity. Each VPC route table needs routes to the peer's CIDR, and the peering relationship is not transitive. Transit Gateway changes the topology. Instead of building many direct VPC to VPC relationships, you connect VPCs, VPNs, and direct connect gateway associations to a central network hub. Transit Gateway route tables then control which attachments can talk to one another. Do not choose Transit Gateway only because you reached a magic number of VPCs. Choose it when you need hub-and-spoke connectivity, transitive routing, centralized route policy, or an architecture that connects many VPCs and on-premises networks. The exam signal is the topology. If the question says, direct connection between two VPCs, think peering. If it says, centralized connectivity and routing across many VPCs and on-premises networks, think Transit Gateway. Transit Gateway acts as a central hub for VPCs and on-premises networks. Each VPC attaches to the Transit Gateway. A site-to-site VPN can attach to it, and a Direct Connect gateway can associate with it for Direct Connect connectivity. The transit gateway route tables then decide which attachments can communicate. That is different from a dense web of VPC peering connections. In a hub-and-spoke design, a new VPC gets one transit gateway attachment instead of a separate peering connection to every existing VPC. For a cloud practitioner scenario, remember the reason to choose it: centralized, scalable routing across VPCs and hybrid networks. It is not just a bigger VPC peering connection. It is the routing hub that gives you the hub-and-spoke model. So which service should you choose? Use VPC peering when you need direct, one-to-one connectivity between two VPCs, and the design does not require transitive routing. It is simple and effective for a small, stable topology. Use transit gateway when many VPCs, on-premises networks, or multiple connectivity types need to communicate through a central hub. It gives you centralized route tables and transitive hub-and-spoke connectivity. Here is the interview-safe answer. Choose the service that matches the network topology. Peering is direct VPC to VPC connectivity. Transit gateway is centralized, scalable connectivity across VPCs and hybrid networks. One practical note: transit gateway is a managed service with attachment and data processing charges, so it is not automatically the right answer for every 2 VPC environment. Use it when the architecture needs its central routing model. You're the cloud network engineer. Your company currently has 3 VPCs. Next year, it expects to have 20. Every VPC needs connectivity to the company's on-premises data center. Some VPCs also need to communicate with other VPCs, and the security team wants centralized control over which networks can communicate. Would you build a web of VPC peering connections? You could create individual peerings for some direct relationships, but the topology becomes increasingly difficult to manage as the environment grows. A better architecture to evaluate is transit gateway. Each VPC attaches to the transit gateway. The on-premises network can connect through site-to-site VPN or through a direct connect gateway association. Transit gateway route tables then determine which attachments can communicate. That gives you a hub-and-spoke architecture instead of a growing web of point-to-point relationships. But don't memorize, lots of VPCs equals transit gateway. Remember the actual requirement. If you need simple, direct connectivity between 2 VPCs, VPC peering may be exactly what you need. If you need centralized, transitive routing across many VPCs and hybrid networks, transit gateway is the architecture to evaluate. The topology determines the service. Think of DNS as the Internet's name system. Your browser knows a domain name such as shop.example.com, but it needs a DNS answer before it can connect to the right destination. That DNS answer might be an IP address, such as an A or AOA record. Or it might be an alias or another DNS record that points the browser toward an AWS resource, such as a CloudFront distribution or load balancer. The important idea is simple. DNS maps human-friendly names to the information clients need to locate a service. Without DNS, users would need to remember addresses and endpoints instead of domain names. In the next scene, we will separate DNS from network routing, because the name Route 53 can make beginners think it is a router. It is not. Route 53 is AWS's highly available DNS service. It can register domain names, answer DNS queries, route DNS traffic to resources, and perform health checks. When a user enters your domain name, Route 53 provides the DNS answer that directs the user toward your application. That answer might be a raw IP address, but in AWS, it is often an alias record pointing to a CloudFront distribution, load balancer, API gateway endpoint, or another supported resource. Do not let the word route confuse you. Route 53 does not forward your application packets like a network router. It answers DNS queries and can apply routing policies based on factors such as health, latency, geography, or weighted traffic distribution. For the exam, the memory trigger is this. If the question asks which service maps a custom domain to an AWS application or manages DNS routing, the answer is Route 53. When you need to point a domain at a new destination, the practical process is simple. Open the Route 53 console, find the hosted zone for the domain, locate the record that needs to change, update the record value or alias target, and save the change. Then test the DNS answer and allow for caching based on the record's time to live setting. The target might be an IP address for an A record, another host name for a C name record, or an AWS alias target, such as a CloudFront distribution or application load balancer. The right record type depends on the destination. For the exam, you do not need to memorize console clicks or CLI flags. You need to recognize that Route 53 is where DNS records and DNS routing behavior are configured, not the VPC console. Imagine a viewer requesting a product image or a dynamic web page from an origin far away. Without a content delivery network, each request may travel all the way back to that origin. CloudFront is AWS's content delivery network. It speeds up delivery of static and dynamic web content by routing viewers to nearby edge locations. If eligible content is already cached at the edge, CloudFront can serve it immediately. If the content is not available there, CloudFront requests it from the configured origin. That origin might be an S3 bucket, an application load balancer, API gateway, media package, or another HTTP server. The origin remains the definitive source of the content. CloudFront distributes and caches copies according to your configuration. The memory trigger is simple. Route 53 is about names. CloudFront is about fast content delivery. In the CloudFront console, choose Create Distribution and select an origin. The origin might be an S3 bucket, a load balancer, API gateway, or another HTTP server. That is where CloudFront retrieves content when it does not have a usable cached copy at an edge location. Then configure the viewer and cache behavior you need, review the settings, and create the distribution. CloudFront assigns a distribution domain name. You can use that domain name directly, or point your own custom domain to the distribution with a Route 53 alias record or the appropriate DNS record type. The key concept is the flow. Viewer requests content. CloudFront serves a cached response when available, and CloudFront contacts the origin when it needs the definitive content. After creation, wait until the distribution's deployment status shows that it is ready before testing it. Do not promise a fixed deployment time in the narration. Configuration changes and distribution deployment can take time. Let's troubleshoot another scenario. Your company runs an e-commerce site in AWS. Customers can successfully open shop.example.com. DNS resolution works. Route 53 is returning the correct destination. But customers on the other side of the world complain that product images and static files load slowly. Should you redesign Route 53 to make the content faster? Not necessarily. DNS is already doing its job. The users can resolve the name and reach the application. The problem is content delivery. That's where CloudFront comes in. Put CloudFront in front of the appropriate origin and cache-eligible content closer to viewers at edge locations. Now keep the roles separate. Route 53 helps users find the application. CloudFront helps deliver the content efficiently. If the name doesn't resolve correctly, investigate DNS. If the name resolves but globally distributed users need faster content delivery, evaluate CloudFront. That's the difference between troubleshooting the name and troubleshooting the delivery path. For hybrid connectivity over typical public internet paths, a site-to-site VPN creates IPsec encrypted tunnels between your on-premises network and AWS. On the AWS side, the VPN can connect to a virtual private gateway attached to a VPC, or to a transit gateway in a hub-and-spoke design. On your side, the customer gateway device represents your router, firewall, or software VPN appliance. Every AWS site-to-site VPN connection includes 2 tunnels. Configure both tunnels so traffic can fail over if one becomes unavailable. Then make sure the routing is correct. Your VPC or transit gateway route tables need routes for the on-premises network, and your customer gateway needs routes back toward the AWS networks. The exam memory trigger is site-to-site VPN means IPsec encrypted connectivity between on-premises networks and AWS. For private network connectivity between your data center and AWS, Direct Connect provides an alternative to sending traffic over the public internet. The architecture has layers. Your network reaches an AWS Direct Connect location through a cross-connect or a Direct Connect partner. On the Direct Connect connection, you create the appropriate virtual interface. That virtual interface can connect through a Direct Connect gateway to a virtual private gateway, or associate with a transit gateway, depending on the design. For the exam, remember the core distinction. Direct Connect is the private network connectivity option. Site-to-site VPN is the IPsec encrypted tunnel option. But keep one security caveat in your head. Direct Connect is not IPsec encrypted by default. If a scenario requires the Direct Connect path and encryption, look for a design that adds a VPN overlay or MACsec where it is supported. So, which do you pick? Choose site-to-site VPN when you need encrypted connectivity quickly and the application can tolerate the variability of an internet path. It is a common fit for pilots, branch connectivity, and backup paths. Choose Direct Connect when the business needs private network connectivity into AWS, sustained capacity, or a more predictable network experience. It usually takes longer to deploy because physical connectivity, provider coordination, or cross-connect may be required. And remember, they are not always competing choices. A company may use VPN while waiting for Direct Connect, use VPN as a backup to Direct Connect, or run an encrypted VPN overlay over the Direct Connect path. For the exam, match every requirement. Fast and encrypted points toward VPN. Dedicated or private connection with sustained capacity points toward Direct Connect. Private path plus encryption points toward a combined design. When several VPCs and an on-premises data center need to communicate, point-to-point links become difficult to manage. Without a central hub, every new VPC may need more routes and additional direct connectivity relationships. Transit Gateway replaces that sprawl with a hub-and-spoke design. Each VPC attaches to the Transit Gateway. The on-premises network connects through a site-to-site VPN attachment or through a Direct Connect gateway association. Then Transit Gateway route tables determine which VPCs and networks can communicate. This does not mean every VPC can automatically reach every other VPC. The route tables and attachment associations still control the allowed paths. That central policy control is the value of Transit Gateway. The exam pattern is straightforward. Multiple VPCs, on-premises connectivity, and a need for centralized routing usually point to Transit Gateway. Now let's combine several networking concepts. A company has an on-premises data center and 10 AWS VPCs. The requirements are: production traffic needs private network connectivity into AWS. The company transfers large amounts of data every night. Sensitive traffic requires encryption in transit. The VPCs need centralized connectivity. And if the primary network path fails, critical workloads must still reach AWS. What would you design? Start with the primary connection. The private network and sustained capacity requirements point toward Direct Connect. But remember, Direct Connect is not IPsec encrypted by default. If the security requirement calls for encryption on that path, evaluate an appropriate encryption design such as MACsec, where supported, or an IPsec VPN overlay over Direct Connect. Now address the 10 VPCs. Instead of managing separate hybrid connections to every VPC, Transit Gateway can provide the central routing hub. The Direct Connect design can reach the Transit Gateway through a Direct Connect gateway association. Finally, address resilience. A site-to-site VPN can provide an alternate encrypted path over the internet if the primary Direct Connect path becomes unavailable. Now look at the architecture you've created. Direct Connect solves the primary private connectivity and capacity requirement. An encryption mechanism addresses the security requirement. Transit Gateway solves centralized routing. Site-to-site VPN provides an alternate path. This is how AWS architecture questions work. One requirement may point to one service. A complete production design may require several. These 7 networking patterns cover the decisions you'll see repeatedly in cloud practitioner questions. Pattern 1. VPCs, subnets, and route tables. The route table determines the network path. A subnet is public when its associated route table has a route to an internet gateway. Pattern 2. Internet access. For the common IPv4 design, direct internet communication requires the correct route, a public IPv4 address or elastic IP address, and security controls that allow the traffic. Pattern 3. NAT Gateway versus VPC endpoints. Use a public NAT gateway when private subnet resources need general IPv4 internet egress. Use a VPC endpoint when resources need private connectivity to a supported AWS service. Remember, gateway endpoints support S3 and DynamoDB, while interface endpoints use AWS Private Link for many other supported services. Pattern 4. VPC peering versus Transit Gateway. Use peering for direct VPC to VPC connectivity. Use Transit Gateway when the architecture needs centralized, transitive routing across multiple VPCs and hybrid networks. Pattern 5. Route 53. Think names and DNS. Route 53 answers DNS queries and directs users toward configured destinations. Pattern 6. CloudFront. Think content delivery. CloudFront uses AWS's Edge network to deliver eligible content closer to viewers. Pattern 7. Hybrid connectivity. Site-to-site, VPN provides IPsec encrypted connectivity. Direct Connect provides private network connectivity into AWS and greater options for sustained capacity, but it is not IPsec encrypted by default. Don't memorize these as 7 unrelated AWS products. Memorize 7 networking problems. Once you identify the problem, choosing the service becomes much easier. Here is the whole picture. But think of it as connected modules, not one fixed path. First, Route 53 handles the name. It answers the DNS query for your domain and can point users toward a CloudFront distribution, a load balancer, or another configured destination. Second, CloudFront handles content delivery. A viewer connects to CloudFront. CloudFront serves a cached response from an edge location when it can, or retrieves the content from its configured origin, such as S3, a load balancer, API gateway, or an HTTP server when it needs to. Inside a VPC, route tables control the network paths. A public subnet has a route to an internet gateway. A private subnet can use a public NAT gateway for IPv4 internet egress. For private access to S3 or DynamoDB, a gateway endpoint can send that service's traffic without NAT or an internet gateway. Finally, Transit Gateway handles the hub when multiple VPCs or an on-premises network need centralized connectivity. It is not required in every VPC. It is the central routing module for larger cloud and hybrid designs. That is the whole architecture: DNS, content delivery, VPC routing, private service access, and hybrid connectivity, all connected by the route decisions you make. That is the cloud practitioner network in picture. 3 ideas matter most. 1. The route table defines the subnet's path. A route to an internet gateway makes a subnet public. For an IPv4 resource to communicate directly with the internet, it also needs a public address and security controls that allow the traffic. 2. Match connectivity to the destination. Use a public NAT gateway for general IPv4 internet egress from private subnets. Use a gateway endpoint for private S3 or DynamoDB access, and interface endpoints for other supported services. Use Transit Gateway when you need centralized routing across VPCs and on-premises networks. 3. Keep the service roles straight. Route 53 resolves names. CloudFront accelerates content delivery. Site-to-site VPN provides IPsec encrypted hybrid connectivity. Direct Connect provides private network connectivity into AWS, but is not IPsec encrypted by default. If you can explain those 3 ideas, networking questions become service selection exercises instead of memorization traps. Before you leave this video, test whether you actually understand the architecture. Don't spend the next hour memorizing AWS definitions. Instead, find 20 cloud practitioner networking scenario questions. For every question, do one thing before looking at the answers. Identify the networking requirement. Is the question asking for public internet access? Outbound-only internet access from a private subnet? Private access to an AWS service? Direct connectivity between 2 VPCs? Centralized routing across many VPCs? DNS? Global content delivery? Encrypted connectivity to an on-premises network? Or private, high-capacity hybrid connectivity? Once you identify the requirement, then choose the AWS service, Internet Gateway, NAT Gateway, VPC Endpoint, VPC Peering, Transit Gateway, Route 53, CloudFront, Site-to-Site VPN, Direct Connect. That is how you should approach networking questions on CLF C02. Requirement first, service second. And for every question you miss, don't just memorize the correct answer. Explain why every other option is wrong. That's where the real learning happens. Don't finish this networking series by just memorizing AWS service names. Build the architecture. Here's your portfolio challenge. Create a VPC using an address range such as 10.0.0.0/16. Inside it, design at least 2 subnets. A public subnet and a private subnet. Attach an internet gateway to the VPC Create the route tables. Give the public subnet a default route to the Internet Gateway. Then create a public NAT Gateway in the public subnet and configure the private subnet's IPv4 Internet-bound traffic to use it. Now add an S3 gateway endpoint. Look at the private subnet's route table and understand why S3 traffic can use the endpoint, while general Internet traffic can still use the NAT Gateway. If you want hands-on practice, deploy test resources only where appropriate and watch the cost of services such as NAT Gateway. Then extend the architecture on paper or in a diagram. Add Route 53 for DNS. Add CloudFront for content delivery. Add a second VPC and decide whether VPC peering makes sense. Then expand the design to several VPCs and replace the point-to-point model with Transit Gateway. Finally, add an on-premises data center. Show site-to-site VPN as the encrypted internet-based hybrid path. Show Direct Connect as the private connectivity option. And show how Transit Gateway can become the central routing hub connecting the environment. Now document the project. Include your architecture diagram. Include your CIDR ranges. Include the public and private route tables. Explain why the NAT Gateway is in the public subnet. Explain when you would use a VPC endpoint instead of NAT. Explain when you would choose peering instead of Transit Gateway. And explain when you would choose VPN Direct Connect or both. Put the project in GitHub or your portfolio. Now imagine you're in an interview and someone asks, "How does AWS networking work?" You don't have to recite definitions. You can show them an architecture you designed and explain exactly how the traffic flows. That's the goal. Careers aren't built by watching videos. They're built by applying what you learn. Go build it. Document it, and be ready to explain your decisions. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.